Good evening, everyone. Thank you for joining me. I'm Mr. Ish. Inverse trigonometric function graphs with derivative correlations. Nothing too fancy or hip, but very interesting material. Inverse sine, arcsine, as you know, graph. What does it look like? You know everything stems off based on originally from the trigonometric functions, then you're doing their inverse relationships, so you're getting the arc or the inverse characteristic. When you're looking at the inverse sine, it has a graph which looks something like this, and I'm going to bring it out for you. You have pi over 2 minus pi over 2, you have minus 1, 1. You see how the domain and the ranges have flipped around with regards to the sine function. You have the radians along the x-axis, you have the numerical items such as 1 and minus 1 along the y-axis. Here everything is flipped around. You have a function graph for the inverse sine which looks something like that. Think about it. That's exactly what it looks like. What would be a good derivative correlation for something like this? If you were to draw tangent lines for any point on this, all your tangent lines would be upwards. The slopes of those will always be positives. What exactly is the derivative of the inverse sine or the arcsine? It happens to be a positive one, doesn't it? 1 over root 1 minus x squared. That right there is your graph. Now, when you're looking at the inverse trigonometric functions, you know this has a certain reciprocal. It looks like that. What would the graph look like with regards to what you're seeing? Well, these pi over 2 minus pi over 2, 1 minus 1 stay exactly the same. But you know that inverse sine, you know this arcsine of 0 is always equal to 0. You can't do that with regards to a reciprocal. You get an undefined. What does that tell you? With regards to this x-axis, it has now become a horizontal asymptote. You have a specific point here. You know the inverse sine or the arcsine of 1 is a pi over 2 because there's a certain angle. If you do it sine, it's 1. That angle is pi over 2. Hence, 1 comma pi over 2 retains over here, minus 1 comma minus pi over 2 retains over here, and those are good points of reference. Everything will become reciprocal with regards to this curve. From this point up here, from this point down here, these will split and they'll become a reciprocal, and you'll have a function which will go like this in terms of your inverse cosecant. Along this horizontal asymptote, you'll have this grazing of that function on either end. But what is an interesting aspect that you're seeing over here? If you were to look at tangent lines, they are sloping downwards. In all instances, you have a downward sloping tangent line. What is the derivative of this cosecant inverse? It's minus 1 over absolute value of x. You have here x squared minus 1. We're not worrying about the absolute value. The reason for that is a material for another video, but we're worrying here about the sine, minus 1. You see here with the arc sine or the inverse sine, tangents are always positive with regards to the slopes. With the arc cosecant or inverse cosecant, tangents are always negative, hence you have that minus. We will talk about this aspect, the absolute value, in another video. But we're just showing you the graphs of these with these derivative correlations, which means how does a derivative correlate to the graph you see by means of the slopes of the tangents. I've shown you this arcsine and arccosecant. What remains now is to show you the arccosine and the arcsecant. When you look at the inverse cosine or the arccosine, you have a bunch of values. You can say 1 and minus 1. You can say over here a pi over 2, and you can say pi. The graph of this looks like this. You have minus 1 with pi, you have 0 with pi over 2, and you have 1 with 0. Your function curve would look like that. When you are going to look at it in terms of the derivative, you know the derivative of this is not hard. It's going to be equal to minus 1 over root 1 minus x squared. Now in this particular instance, you're looking at these tangent lines. They're always downward sloping, hence you're having a negative sign show up here in terms of the derivative of this function, the arc cosine or the inverse cosine. You're seeing that. But when you look at everything with regards to the reciprocal of that, you are looking at arcsecant, or you can say secant inverse. These reference points stay the same. You have minus 1, you have 0, you have 1, you have a pi over 2, you have a pi. But you see right over here, if you did arc cosine of, let's say, 0, you would have pi over 2. There's a certain angle, if you did the cosine of it, it's 0, and that angle is pi over 2. This pi over 2 right here will generate a horizontal asymptote, because when you look at it in terms of the reciprocal, the arcsecant, you cannot have an undefined function. It would make it undefined otherwise. Then you reconcile that by means of a horizontal asymptote. This value right here, -1 comma pi, retains as a good reference point. This point right here, 1 comma 0, retains as a good point, and then you have a function which goes in this direction. Now when you look at this specific function in terms of tangent lines, the slopes of the tangent lines are always positive. No matter how you look at it, they're always positive. What is the derivative of the arc secant or the inverse secant? You know the derivative is now a positive one. You have this absolute value. We're not talking about the absolute value here. We will in another video, but not here. And then you'd have x squared minus 1. The slopes of the tangent lines on that function accounts for the positivity here. The slopes of the tangent lines all being negative counts for the negativity over here. And you're seeing that very clearly. That's the derivative correlation based on the graphs that you see. These are important graphs. They are frequently not taught, especially the arcsecant and the arccosecant, but it's very important to know that. What will remain in the future is to determine why in the arccosecant and arcsecant, why do we see this absolute value? What's the reason for that? That'll be an interesting video. I'll post that at some point, not too far away, but I will. And that's all I wanted to show you in this video. Thank you for watching.